Greetings. I'm going to give a brief overview of energy, kinetic, and gravitational potential energy using the energy skate park simulation from PhET. This is an HTML5 simulation, so this will work well on phones and iPads, and in fact would be part of the PhET app. So we're going to start and primarily finish with the introduction screen. And actually it's kind of weird. You can't, once you put the girl up there, she'll go. But then if you stop it, then you can set her up there and she will stay. So we want her to stick to the track. We're going to show the path, the speed, and probably use a stopwatch a little bit later. And notice her mass is 60 kilograms. And over here we have the energy. So right now, notice at the top, she's all potential energy, gravitational potential energy, and no kinetic energy. Well, for one thing, it's frozen. But once we hit start, you'll notice that the bar will be a large amount of potential and almost no kinetic. So as she goes back and forth, notice a few things. Those little pink dots show her path. And there's a little pink dot every so often, every fraction of a second. So notice how the pink dots are closer together at the top, farther apart at the bottom. That's just an indication of lower speed at the top, larger speed at the bottom. Notice that at the top, she has the maximum gravitational potential energy and zero kinetic. At the bottom, she has the maximum kinetic energy and zero potential. So with this simulation, the ground is set at zero gravitational potential. And her max speed is about 10.8 or so. So we can see the bars and notice the total energy. Oh, let's just kind of stop it somewhere in the middle. Notice the total energy does not change. Let's just do a quick calculation of her gravitational potential energy. So gravitational potential energy is mg delta y. And she starts 6 meters above the ground. So m, she's 60 kilograms times g, 9.8 meters per second, times 6 meters. So 3528. And her kinetic energy, 1/2 mv squared. It's kind of hard to tell. The biggest number I saw here for the speed was 10.8. So we'll go 1/2 m. So that is her mass again, times 10.8 squared. And the first answer we got was 3528. And here we get about 3,500. So we didn't use the super precise value for G. I'm not even sure what they use in the coding here. Probably 9.8, maybe 9.81. That would actually get a bigger number for the MGH. The maximum speed was probably a little bit greater than 10.8, but still very close, about 3,500 joules for the maximum kinetic and the maximum gravitational potential. So that all makes sense. And let's time the skater. So from top to top. So about 2.6. And I'm just going to write that down. Pause that. So we've had a 60 kilogram skater. Let's move down to half that mass, 30 kilogram skater. So take a few seconds and predict what things will be different and some things that could be different. So we've got the bars here, kinetic potential, total energy, speed, time it takes for one trip, maybe the pattern of the pink dots. Let's try that out. So we see that the kinetic and potential are still oscillating back and forth, but each bar doesn't get as high and the total energy isn't as high. The speed looks like it maxes at about 10.8 again. So let's try the time. 2.4. Last time I got 2.6, and my timing was not fantastic, I'm sure. So you could decide whether those truly are equal or there's some difference. One thing to think about is this skater's mass is half of the mass before, 30 kilograms versus 60, and the time difference was a slight amount. So you can decide whether that is a physical difference. I'm going to claim that it is not. It's just a factor of me not starting and stopping the clock optimally. So if we could go back to the calculator, but notice each term, mgh, has m to the first power, and kinetic energy 1/2 mv squared has m to the first power. So in each time, it's the same effect for mass. So if we cut the mass in half, the total energy will be cut in half, which kind of makes sense based on this here. We're going to try one more thing. And we're going to go with a different track. And we'll keep her at 30 kilograms. So think about what you were seeing with the bar chart here. Think what you were seeing with the speed and so on, and the time, which we won't do quite yet. But what things will change? Well, she's at the height of 6 meters again. So that seems to be the same. The bars are the same height. It looks like at the bottom, she's about 10.8 for the speed. And now we can do the time, which I should have got that last time. So 3.83. You can again decide, did I not hit the start and stop at the optimal time? Probably didn't, but was not too far off. So the time is greater. The maximum speed is the same, and the maximum potential and kinetic energy are the same, and the total stays the same as well. Let's go back to this track, and now let's add a little bit of friction. And there's no quantitative value here. We'll put her at the top. And now tell me what will change with friction on the track. Right now, the potential bar is the same height as the total bar and the same height as it was when we had no friction. She hasn't gone yet, so we can't say anything about the speed. Let's first off think about what might change. And let's get started. So notice the kinetic and the potential are dancing back and forth, but they're getting smaller and thermal energy is increasing. And notice the maximum speed is decreasing as well. Now she's not getting even above 6 meters per second. And before she was getting above 10 meters per second. Kinetic and potential energy are being converted into thermal energy. Thermal energy here is sort of generic name for the rubbing of a lot of different things. So the wheels on the track, the bearings, the wheels on the bearings, so the wheels are getting a little bit hotter. The axle on the skateboard's getting a little bit hotter. She's colliding with air molecules, so they are moving faster. Some of her energy is transferring to those air molecules. So all that is generically considered thermal energy. You've probably heard the term energy can't be created or destroyed. It's kind of a generic t-shirt slogan, physics statement. And you might be saying, well, look, there is no kinetic energy now, no potential energy. So that was created and destroyed. The longer version of the t-shirt statement is energy can't be created or destroyed, just converted into another form. So we just witnessed the kinetic energy being converted into thermal energy. And we know that the wheels are not going to stay hot forever. The axles are not going to stay hot forever. They are going to cool down by the molecules in the wheels and the axles are jiggling back and forth and causing the air molecules around them to jiggle faster, which causes the air molecules around them to jiggle faster, and so on. So pretty soon the effect isn't noticeable in real life. We're not going to get great amounts of warming because this 30 kilogram girl is going back and forth on a skate track. But yeah, this is one thing that is different with friction. So kinetic energy and potential energy are not conserved in this case. And in the physics language, we actually talk about work being done. So friction is what's called a non-conservative force. So friction is doing work on the skater and the skateboard. And in general, the the energy conservation formula, kind of got a weird brain freeze there. The energy conservation formula would say that the delta KE plus delta PE, so the change in kinetic energy, the change in potential energy, equals zero if there's no work done by non-conservative forces. But if there is work being done by conservative forces, then that zero is replaced by the work done by non-conservative forces. So energy is still conserved if we broaden the term to include thermal energy in this case. So that is just a brief overview of energy. Hopefully that was a good introduction to the concept and will help you kind of see things, and feel free to go to the PhET simulation and try some of these things yourself.